So this is a field theory project, and Alberto Cattaneo will talk about the BV formalism.
Okay, so thanks. So we'll give you a very, very short presentation about what I've been doing for several years, and especially what I've been doing in the last few years, together with several collaborators, both senior and junior collaborators, some in my group and some elsewhere. So let me just start with a very short history of the BV formalism. So this was developed by Batalin and Wilkowiski in the late 80s and late 70s and early 80s. And the idea was that of extending and generalizing the procedure by Fadeev Popov and by Becker, Westphal, and Tutti for the gauge fixing of quantum gauge theories. And the main point was to have a way to establish the independence on the choice of gauge fixing. Some more relevant work was done by Jean Justin in the 80s, where he was able to relate questions about the renormalizability of field theories to cohomological questions, so more mathematically algebraic cohomological questions in the BV formalism. And he has a very influential book. So this was actually the main topic for the Belgian school, and this probably culminated with the book by Hanno Teitelboim in the early 90s, which was somehow the reference text for several years to come, even decades. And since the 2000, there have been a BV renaissance, probably at the beginning motivated by Kontsevich's deformation quantization, which secretly relies on BV ideas. And this actually was then developed by myself together with Giovanni Felder, where we applied these BV ideas to the Poisson-Sigma model, and we used several BV ideas to get new results about deformation quantizations. Then there was the group by Lossev and Menioff, where they developed the Wilson renormalization for field theories, but for a particular class of discrete field theories. This was then put in a more general context by Costello, and who, together with William, was also able to relate this to a formulation of quantum field theory, quantum BV theory, in terms of so-called factorization algebras. Then I mentioned my program with Pavel Menioff and Nikolai Reshetikin, where we related this, the renormalization, with renormalization, the BV formalism more mathematically to push forward of BV theory and showed how it is related to homotopy transfer. And we focused on the quantization of theories on manifold with boundary. And then finally, let me mention the algebraic geometry counterpart of BV. This is called derived symplectic geometry. It's been developed by Panretwan, Bakiewiczozis, and more recently also by Damian Kalak. So here, on this technical slide, let me give you in 1 minute the main idea of BV. So these are all related about supermanifolds with symplectic structure. Supermanifold means manifold where you also have some odd non-commutative, anti-commutative coordinates. So the idea is that you start with an odd symplectic manifold, which means the symplectic structure is odd with respect to internal grading. And the first main result is that the half densities on non-symplectic manifolds, so these are things whose square can be integrated, actually can directly be integrated on Lagrangian manifold. And the second main technical result is that there is a canonical second order operator acting on half densities. And the last result is that if you take a delta closed half densities, then its integral is invariant under deformations of the underlying Lagrangian submanifold. So these are the three technical results, and can be regarded as an extension of Stokes' theorem to the realm of supermanifolds. And the main usage in field theory is that you start with some ill-defined integral, is defined because the integration domain, this Lagrangian submanifold, is not the right one to make the integration, and then you deform this Lagrangian submanifold to some Lagrangian submanifold nearby on which the integral is well defined. And these previous results said that the result does depend on the choice of the Lagrangian submanifold, at least locally. So this is very similar in spirit to, for example, when you want to compute the self-intersection number of a half-dimensional manifold. So the idea that if you take its intersection with itself, then of course you have infinitely many intersection points that there is nothing you can do. But if you slightly deform one of the two copies of this submanifold, then you can arrange things in such a way that you have only finitely many transversal intersection points, and then you can compute the intersection number with sign there. You just sum and you get a well-defined number, and then it's easy to show that this does not depend on how you deform your submanifold. So this is essentially the same idea. And now let me tell you what we did, especially for manifold with boundaries and corners. So first thing we realized that actually you start with a BV theory for your quantum field theory, and then you get a whole hierarchy of BV-like theories associated to the corners of increasing dimension. By BV-like, I mean essentially BV, but with some shift in parity and degree. And then if you reinterpret things geometrically, you see that, for example, on the boundary of your field theory, you get some symplectic structure, which is what to describe what in physics called reduced phase space. And then if you go to corners, you get Poisson structures and so on. And actually, this idea was later generalized by Damian Kalak in the third notion of a derived intersection in the language of derived symplectic geometry. We also were able to quantize several field theories in this setting. So for example, show that the quantization in the bulk produces a cohomology class of a state on the boundary. So the cohomology class is actually the physical state. And then we showed also that, well, this procedure is not just a game. Actually, it's useful because the idea that, for example, you can start with a manifold on which you compute a partition function, you cut it into some manifolds with boundary, you compute the states, and then you pair the states, and this gives you the partition function for the whole manifold. So this somehow procedure is sometimes easier. And here are the explicit results we had. So for example, we were able to apply this procedure to AKZ theories. So this includes the Poisson-Sigma model and Chern-Simons theory, quantum mechanics, topological quantum mechanics, some version of discretized abelian Beer theory. And then, well, some other people working on this, like Pavlov and some other collaborators, were also able to do two-dimensional Yang-Mills theory and two-dimensional interacting field theory. And finally, we've been able to approach classical gravity, both in the Einstein-Hilbert and the Palatini-Cartan version. And here the goal is to understand, for example, the corner structure, the Poisson structure associated with the corner. And some further goals include, of course, more physical theory, like Yang-Mills theories, including also spinor fields, and to understand better holography. So, for example, the relation between Chern-Simons and West-Domino-Wipton, and also a generalization to other theories. And finally, to understand better these Poisson structures on the corners and their relation to the algebra of currents. So this is the end of the presentation, and well, I can say more for answering questions.
Okay, thanks a lot. I have one maybe not very concrete question, but how is it? So you said that one of the ideas is that one can cut, say, the space into pieces, and then associate to those pieces some objects, and then glue back together.
Yes.
At the moment, for which theories can one do it? For which theories are realistic from that perspective?
Okay, so well, okay, so there is one obstruction that you can expect is that somehow related to anomaly, essentially probably the same origin as the usual anomalies you find in field theory. Basically, okay, first of all, well, you have to, there are some minimal regularity conditions that you have to assume for this to work. Of course, if you do it for more physical theory, you have to take also renormalization into account. This is something we haven't done yet, but the formalism is ready to do that. The main problem is that the quantum boundary theory, what you get is some candidate for the coboundary operator that is needed to define this cohomology class. And but nobody assures you a priori that this really squares to zero, that it's really a coboundary operator. And there might be cohomological obstruction into making it into a coboundary operator. But these cohomological obstruction are well known, essentially are related to the anomalies in quantum field theory. So this is somehow the main problem. If the theory is not anomalous, then you might expect that it works, but of course, I mean, some difficulties may arise. I mean, some more singularities may arise, but in principle, it could be doable. I mean, it could be a lot of work, but in principle, it should be doable.
But for instance, of course, the Chern-Simons theory is famous for like kind of some of its definitions are probably by gluing.
Yes.
So can one now do the gluing of the Chern-Simons theory using this technology?
Well, we've been able to do it, and of course, in a very okay. So that's the starting of it. We've been able to do it. We've been able to compute the state at the first non-trivial order, first non-trivial perturbative order, and we just focused on the case where the bulk is a solid torus. But in this case, we're able to prove that we can compute the boundary state. We have this boundary operator, and then we can glue two tori together, and we can get the three manifolds invariant associated, for example, to length spaces. Actually, this procedure gave a new way to compute the invariant for length spaces. And in principle, this could be performed also at higher order and for less trivial bulks. I mean, there is no technical obstruction, just might be difficult, but there is no a priori obstruction in doing this.
So Alberto, there was this idea that for topological quantum field theory, one could kind of reduce everything to a point, and somehow the object that you associate to a point should contain the whole information. Can you do it in this formalism?
Well, this idea was somehow a definition or a dream, and it is being realized in certain theories, not in others. I think for Chern-Simons, done like in the, well, what should be the non-perturbative version, I think people haven't been able to reduce it to a point yet. I think probably to one dimension.
But you have a perturbative version of that.
Yeah, this would be the perturbative version. So for the perturbative version, well, we have some sort of classical way. I mean, this definition of quantum field theory relies on the functor from some category to another category. And the quantum version is when the target category is the category of Hilbert spaces. And of course, we have a version where the target is well, symplectic structure on super manifold with additional data. And this works. For all these theories, we can reduce to a point. So at the classical level, this theory really reduces to the point. At the quantum level, we've been able to do the quantization only for the boundary in most cases. There are two examples. Actually, there are one important example, two examples, two-dimensional BF theory and two-dimensional Mills theory, where Pavel Nyof and Ricardo Irazo have been able to push the things out down to the corners. So this has been done in this example, two-dimensional BF theories, but not only that, also in two-dimensional Mills theory, which is non-topological, they've been able to push things down to corners and to reconstruct the theory using all the structure down to the corner. For the general situation, this also another of the goals. We would like to understand how to push down the quantization to higher codimensional corners. And I mean, there are ideas essentially, well, trying to generalize what happened in these two-dimensional examples, and I mean, we already have some partial results, but it's a bit too early to see how this will work.
Okay. Thank you very much for this presentation of these very interesting results.